read this problem and let me know what do you understand with respect to a flow time and with respect to capacity. This is narrative representation of the problem. Always we like graphical representation, tabular representation, or mathematical representation better than narrative representation. We have a product. It has two parts, roof and base. Roof goes through two activities and base goes through three activities, and then they come to this point. They will be assembled, they form a complete product, and they go out. Activity 1 takes 15 minutes, and it is done on a human and capital resource called R-punch. This activity takes 8 minutes, and the resource, human resource and capital resource allocated to this activity is called R4. Activity B punch takes 3 minutes, and human and capital resources allocated to this activity are called B punch. B4 takes 10 minutes, and welding takes 12 minutes. Final assembly, 10 minutes. This information, what is the flow time of this process from where we start to where we finish. I should define two terms with respect to flow time: theoretical flow time and flow time. Theoretical flow time only include value-added activities and those things which we show them by rectangle. However, beside actual activities, besides value-added activities, we also have waiting lines, inventories. Those we show them by triangles. We have not considered them. At all of these points, we may have some inventory. So whenever I talk about flow time, that includes triangles and rectangles. If we do not want to talk about rectangles, then we are talking theoretical flow time. What is the theoretical flow time of this process? How long does it take to complete one single product, which is composed of two parts? One part roof goes through this path, one part base this path. They will get assembled and go out. What is the flow time of this process? We have two passes, upper pass and lower pass. The upper pass is to produce roof, the lower pass to produce base. Roof will go through this activity, 15 minutes, this activity, 8 minutes. After 23 minutes, roof is over there. Base, 3 plus 10, 13, 13 plus 12, 25. So base after 25 minutes is there. But in order to assemble them, they both should be there. Therefore, both of them are there in minute 25, right? And then we will have 10 minutes assembly, and 35 minutes is the theoretical flow time. Roof pass, 15 plus 8, 23. Base pass, 3, 10, 12, 25. Both passes, the maximum of those two, which is 25. 25 plus 10 is 35. We call it critical pass, which is the maximum of this pass, which is 33, and this pass, which is 35, and critical pass is 35 minutes. Theoretical flow time is 35 minutes, but flow time will be theoretical flow time plus the time the parts may spend in waiting lines, in inventories and buffers. Theoretical flow time is 35 minutes. Flow time may be 35 days. Maybe the parts from the minute they come into this factory until the minute they become a finished product, maybe there are therefore 35 days. Therefore, the ratio of flow time to theoretical flow time usually is quite high. Something around 10 times, 20 times, 100 times, 200 times, and things like that. When you go to see your doctor, maybe you see him for 5 minutes. But from the time that you go there until the time that you come out, it may take 2 hours. Now, if we have a process like this, where activities cannot be broken down into smaller pieces, they are what they are. R punch, activity R punch is 15 minutes. Activity R punch has been allocated to resource R punch, which is a combination of human and capital resources. Activity R form is 8 minutes. This activity has been allocated to resource R form, and the load of resource R form is 8 minutes because this activity takes 8 minutes. Each individual activity has been allocated to a separate human and capital resource. So these 6 activities, they share no human, no capital resources. And we have 1 unit of human and capital resource for each of these. What is the capacity of this process? How many garage doors per day can be produced? Let me once again introduce you to a couple of definitions. This is activity time. It is 3 minutes. This activity has been assigned to this resource. When it is assigned to a resource, we call it unit load. In this specific example, in this situation, activity time for B punch is 3 minutes. Unit load of B punch resource is also 3 minutes. If 2 activities of B punch and R punch, they were assigned both of them to one single machine. Suppose the name of the machine was punch. If this activity of B punch and this activity of R punch, they both were allocated to this resource, then activity of R punch was 15 minutes. Activity of B punch was 3 minutes. But unit load of punch resource was 3 plus 15, which is 18 minutes. We refer to unit load as TP. This much time is allocated to that resource. We show it by TP. Let's take a look at R punch resource. In 15 minutes, I can complete 1 unit of product. In 1 minute, how many units I can complete? Equal to 1 over 15. Therefore, if it takes 15 minutes to complete a job, if load of a resource is 15 minutes, each minute it can produce 1 over 15 product. And I can multiply this by 60, and in 1 hour, this can produce 4 units of product. Therefore, as long as I have 1 resource, capacity, which I show it by RP, is equal to 1 over TP. Here capacity is 1 over 15. Here capacity is 1 over 8. Here capacity is 1 over 3. Here capacity is 1 over 10, and here capacity is 1 over 12 and 1 over 10. This is capacity per minute. We can multiply each one by 60 and get capacity per hour. So we have 6 activities and 6 different resources. We call them resource unit. We have 6 resource pools. In each resource pool, we have 1 resource unit. Each activity has been assigned to a separate resource unit and resource. Later on, we may see that we have a resource pool where there are several resource units doing exactly the same job, correct? Now, if I'm going to compute the capacity of this process, capacity of our punch is 1 over 15 per minute. I can multiply it by 60 for per hour. On the same line of reasoning, capacity of B form 1 over 8 or 7.5 per hour. Capacity of B punch 1 over 3 per minute or 20 per hour. B form 6 per hour. Welding 5 per hour and assembly 6 per hour. Where is the bottleneck? Our punch. Understanding bottleneck is very important in process analysis, because if I don't understand the bottleneck, I may go over there and partition my time and effort into 6 and allocate 1/6 of my time and effort to these activities and resources, while only improving this one can increase capacity. These 5 other resources, if I spend time, improve them, I will not be able to increase the capacity of the process. Process is a chain. Capability of the chain will be defined by its weakest link. The other links, as long as there is a weak link over there, do not play a role. Improving them will not help us. The bottleneck is our punch. Capacity of the process is 4. Now we want to improve the capacity. One simple way is to double the capacity of our punch to go and get a new resource. Before going there, let's talk about a concept called utilization. Utilization is throughput of the resource divided by its capacity. No resource can perform at 100% capacity, but for a minute, let's assume that our punch can work at 100% capacity. If our punch can work at 100% capacity, which is 4 per hour, then what is the utilization of the process and what is the utilization of each of the resources? Utilization is defined as R, which is throughput, divided by RP, which is capacity. In this example, we said, suppose our punch can perform at 100% capacity, therefore R is 4. And we have RP of each of those resources. Obviously, RP of our punch is 4, and therefore our punch is performing at 100% capacity. No process can perform at 100% capacity. Maybe it can perform for 1 hour, 1 day, 1 week, but not on a continual basis, and we will discuss it later. Now compute utilization of each of these resources. So if the process is working at 100% capacity, for the R punch, it is R divided by RP, 4 divided by 4, 100%. R form, 4 divided by 7.5, 53 point something percent. B punch, 4 divided by 20, 20%. B form, 67%. Welding, 80%. Assembly, 67%. But no process can perform at 100% capacity. If it performs, these are utilizations. And now, up to now, we have talked TP and RP which in case of one resource is 1 over TP. And R is always less than RP. It cannot be equal in long time. And utilization is equal to R divided by RP. We can also talk about something called safety capacity. Safety capacity is the gap between RP and R. Safety capacity is absolute, the gap between RP and R. Utilization is relative, the ratio of R to RP. We have utilization of all resources. We learned that one way of increasing capacity is to increase the level of the resource. If you have one resource, buy a second one. If you have two resources, buy the third one. Nothing has happened here, correct? All capacities in those resources will remain the same, and we had them. So all these numbers, 7.5, 20, 6, 5, and 6 will remain the same. The only thing which changes is capacity of our punch is 1 over 15 per minute, correct? But that is the capacity of 1 hour punch. We do have 2 hour punches, so the capacity is 1 over 15 and 1 over 15. Therefore, capacity is equal to 2 over 15. And 2 over 15, when I multiply it by 60, will be 8 per hour. We said capacity is 1 over 15 plus 1 over 15, which is 2 over 15. If I have a single machine, RP is equal to 1 divided by TP. Now, if I have two machines, it is 2 divided by TP. If I have C machines, small c, RP is equal to C divided by TP. C is the number of resources, TP is unit load. RP is equal to C divided by TP. 8 per hour, 7.5, 26, 5, 6. Where is the bottleneck? Welding, right? What is the capacity of the system? 5 per hour. So what happened when we bought one new R punch? What is a managerial observation? What we see here is we doubled the capacity of the bottleneck, but capacity of the process did not get doubled. Capacity of the process from 4 to 5. That is only 25% increase. So we doubled the capacity of the bottleneck, but capacity of the process did not get doubled. Just went up by 25%. There are two managerial takeaways here. One, bottleneck shifts from one place to the next place. As soon as we find the bottleneck and relax it, another place becomes bottleneck. That is one understanding. Always we should find the bottleneck, relax it, look for the next bottleneck. Relax it, look for the next bottleneck. That is one observation. The second observation is something like what you learned in a microeconomic course. You learned diminishing marginal return. You learned that if this is input and if that is output, if you double the input, output will not go out and becomes doubled. That is what we call it, diminishing marginal return. If you remember your microeconomic professor said, if you add labor and labor and labor, then land, there will be not enough land for these people to work. So bottleneck shifts from labor to land. And that is what, when you increase input, output will not go out proportionally. We doubled the bottleneck. Capacity of the process went up only by 25% because bottleneck shifts from one place to the next place, and this is an experiment of the rule of diminishing marginal return. Now suppose instead of buying a new R-punch, we do this. We train both resources to be able to do the same job, right? Usually when we do something like that, when we transform a special purpose machine, a special purpose resource in a general purpose resource, usually this 15 minutes, for example, becomes 17 minutes. These 3 minutes will become 4 minutes. Why? Because when you are supposed to do several jobs, you are not as fast as doing a single. If you don't agree, try to do like this. Try to build 50 squares. Find it out how long does it take. Then build 50 diamonds. Find it out how long does it take. Then build 50 hearts. 50, I don't know. If you do it like this, if you go this way and this way and this way and this way, you do it very fast because you will become specialized in doing a square. You become specialized in doing diamond. You will become specialized in doing heart. However, if you do it like this, draw this one, then 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 this one, you will see it takes much more time to go horizontally compared to vertically. And that is the cost of flexibility. Because if you produce 50 squares, maybe there is no demand for them. Those 50 squares should remain in your company for a long while. But if you produce just 1 square, and then 1 diamond, and then 1, then you are moving with the market. So flexibility usually needs more time. When you have a flexible process compared to a special purpose process, the flexible process usually gets a little bit more time. However, because you are taking advantage of the idleness of some resources, capacity still may go up. Therefore, in this situation, while this 15 may become 16 or 17, or this 3 may become 4 or 3.5 or something, we just leave them as they are, just for the purpose of simplicity, not to go through, not to change the numbers. If that is the case, now compute the capacity of the process. What is the capacity of this process? Okay, let's see where we are now. Now we have 1 punch machine. 2 different activities of R punch and B punch have been assigned to this resource. Here is when activity time differs from unit load. Activity time 15 minutes. Activity time 3 minutes. Activity time of R punch is 15 minutes. Activity time of B punch activity is 3 minutes. They both together are 18 minutes, which is the unit load assigned to punch machines, correct? Therefore, now I can do my computations. All these things will remain the same. The only difference is here, right? The only difference is over there, right? TP, unit load of punch machine, is 18 minutes, correct? C, number of punch machines are 2. Therefore, throughput of this resource pool, which has 2 resource units, is C divided by TP. 2 divided by 18, right? Punch machine, R form, B form, weld, and assembly. What is the new capacity? 5. Where is the bottleneck? Here, right? Therefore, we were able to increase the capacity from 4 to 5 in 2 different ways. One, by buying a new machine, by buying a new resource unit. 2, by cross-training the available resource units and create a resource pool. Which one is cheaper? Usually, cross-training is cheaper than buying new resource units. Cross-training and pooling can increase capacity. Usually, cost of cross-training and pooling. Pooling means to bring different resource units with minor changes and create a resource pool. Each one of them now can do any of the activities as assigned to this resource pool. Usually, cost of cross-training and pooling is lower than cost of adding second resource units. Okay. So during a numerical example, we try to bring to the table several managerial observations. Bottlenecks move from one resource pool to another. By doubling a bottleneck, we cannot increase the capacity of the process and make it doubled because of the rule of diminishing marginal return. Beside increasing the level of resources, beside buying new resources, an alternative way to increase capacity is cross-train resources and pool the capital resources. Cross-train human resources and pool the capital resources. That can also increase capacity. And usually, cost of cross-training and pooling is much lower than cost of increasing the level of activity. But shouldn't forget that when we pool and cross-train, activity times slightly go up. However, because we are using the empty capacity of non-bottleneck resources, the process capacity may go up. One other way of improving the capacity is to focus on TP. Up to now, we focused on C, and we tried to increase C, either by buying a new machine or by cross-training and change C from 1 to 2 and 3 and so on. But the other possibility is to focus on TP and try to reduce TP. How can I reduce TP? By implementing better methods, by training my employees, by using technology, by better management. So I can buy a better machine and reduce TP. I can have better management, a better facility layout to put raw material, finished good, final product, and machines and human resources in a better arrangement to create a smooth flow throughout the process. By improving better methods, how to do the job in a way that the quality is retained but the time goes down, and by training. Now suppose through training, through better method, through some changes in technology, buying new jigs and fixtures and so on and so forth, and by improving the management, a better layout of that station, suppose we were able to reduce GP of welding from 12 to 10, right? What is the new capacity? Again, we can compute capacities and we will find it out that the capacity is 6. But this 6 is a very difficult 6. Why it is a very difficult 6? Because we have 3 resources: beform, weld, and assembly. They all should perform at 100% capacity for this process to produce 6 products per hour. Maybe one bottleneck can produce at capacity or very close to capacity, maybe for one bottleneck. But this probability for 2 bottlenecks goes significantly down. For 3, it will definitely go even lower. Therefore, the larger the number of bottlenecks, the more unlikely to be able to achieve the full capacity. Here, we also observe another difficulty, not on the capacity side, but on the flow side. Now, we have 2 passes. Each of them takes 23 minutes. We have this pass for 23 minutes. And this pass for 23 minutes. We have a lecture this week. You watch it, and it shows us such a system when there are 2 passes with 23 minutes and 1 activity with 10 minutes. Such a network can never be completed in 33 minutes. It will take much more time than 33 minutes. A process like this, if this is 23 and this is 10, is likely on average to be completed in 33 minutes. But a process like this is very unlikely to be completed in 23 minutes. Why? Because the coordination you need to make between these 2 passes. You need to coordinate them such that none of them is more than 23. In real life, they do not take 23. They may take 18, may take 26, right? There is a project management lecture. I have it on YouTube, 2 project management lectures. We assume all activities have uniform distribution. Of course, they are not deterministic. We assume they have uniform distribution. This is uniform distribution. You should remember from your statistic course. And then we show that there is a significant difference between this project, which has 2 activities of the same length. The length of the project will be much smaller in this project. came to this project, when we also have the responsibility of coordinating these two activities. And this one is even more difficult because here we only have one red resource and one green resource and one blue resource, and we want to complete this job, and it takes much more than 120 days that we expect. In project management, in process flow analysis, you can look at them as process or as project. The same rules and regulations are there. Let us summarize what we learned in this lecture. We learned when we relax a bottleneck resource, the bottleneck shifts to another resource. We learned by doubling the bottleneck resource, the capacity usually does not get doubled. This could be interpreted as diminishing marginal return. One other way to increase capacity is cross-training for human resources and pooling for capital resources. Usually, the cost of cross-training and pooling is lower than the cost of adding additional resource units. One other way to increase capacity is to reduce unit load. This is done by better management, better methods, training, replacing human resources by capital resources, more advanced technology, and so on. Processes cannot work at 100% capacity. Capacity is perishable product. It is lost if input is not ready. The more bottleneck resources, the lower the utilization, the lower the capacity, the probability that we achieve a high utilization. Convergence points are important in processes and in projects to manage flow time. The more convergence point, the higher the probability of flow time to exceed the average flow time. Thank you very much.